Okay, so you're doubtlessly familiar with the term critical values, right? Critical values of a function. Right? You've studied maxima and minima. You studied inflection points. All of this was in the context of single variable calculus. Single variable calculus. The functions you dealt with were functions of one variable. Functions of Now, if you recall, all you had to do to find the critical points was you had to set f prime x equals 0 and then find the critical points. Right, so what we're going to do is we're going to do something similar in terms of multivariable functions, right? In terms of now we will start with functions of two variables. But what we do will be applicable to functions of as many variables as you want. Okay, so let's start with a few definitions first, right? So we need to define the terms local minimum and absolute minimum. Right? We need to distinguish between the two. So if you recall in single variable calculus, we're going to look at local minimum maximum and absolute minimum maximum, right? So the points P and Q are local maxima, right? P and Q are local maxima. R is a global maxima. Of course, in the range, this is, so let this be fx, let this be x equals a, and let this point be x equals b. Right? So so this R is a global maxima on a comma v. What is a local maximum? Actually, maxima is plural of maximum, so you should write this as a global maximum. Right, the singular is maximum. Okay, so why is P a local maximum and why is Q a local maximum? A local maximum is a point around which, for which you have for which you can build a range around. So let this point be x1, and let this point be x2, right? So on x1 on this range, P is f is maximum at P, right? F is maximum at P. Now, so and of course on this range, the x, let's call this x3, let's call this, I don't know, x4, right? So on x3 comma x4, f is maximum at Q. So notice what we're doing here. Notice what's going on here. P and Q are the highest points in certain localized subsets of the domain of the function, right? Let me repeat that. P and Q are the maxima on subsets of the domain of the function, but R is a maximum. Sorry about that. R is the maximum of f on a comma b. R is the maximum on the entire domain. So that is why R is known as a global maximum and P and Q are known as local maxima. Okay, so we can come up with a completely analogous definition for multivariable calculus, for multivariable functions. So if you have z equals f of x, y, actually let me open this book with a so I can edit it. Okay, so let's get to our chapter. Just the geometry space. Okay, let's see what's going on in multivariable calculus. Just a moment, please. Okay, so z equals fxy is a surface. Is a surface, and f is defined on a domain D that is a subset of R2. Now, this point here, alright, let's call this point P. Point P is a local maximum. Why is point P a local maximum? Well, because point P is the highest at P. F takes its highest value at point P in a subset of the domain, right? In a subset of the domain, meaning at all points. So let this be actually let x be equal to a and y be equal to b. So in mathematical language, what we would say is that P, there is a neighborhood around P, which is of course a subset of the domain, right? Where f of AB is greater than f of xy. There exists a neighborhood around P, right? Such that f of AB is greater than or equal to f of xy in that neighborhood, right? So that's what the definition tells you. A function of two variables, right, has a local maximum at AB if f of AB is greater than or equal to f of xy when xy is near AB, meaning there is a small neighborhood around AB, right? And that neighborhood is a disk with center AB. This means that f of xy is less than or equal to f of AB for all points xy in some disk with center AB. And of course, the number FAB is called the local maximum value. And similarly, if f of xy is greater than or equal to f av in that neighborhood, near av, then f has a local minimum at av, and av is a local minimum value. Alright, so these are of course defined, these ideas of local minimum and local maximum, these are defined in an analogous fashion to the notions of local maximum and local minimum in single variable calculus. But in this case, the domain is a disk, right? The neighborhood is a disk. Sorry, not the domain. The neighborhood is a disk. In single variable calculus, the neighborhood is a line. Okay. All right. So let's. Now, how do we find these critical points? All right. Now, in single variable calculus, you are used to finding critical. Okay, how do we find maxima and minima? Right. Specifically, there are three types of critical points, but first of all we're interested in maxima and minima. Right. So in single variable calculus, if you had fx, some function of x, right? Fx, what you would do is you would find dy by dx, set it equal to 0, right? And this would gives you your critical points, right? But how would you do this in if you had a function of two variables? Well, the way to look at this is to okay, and this is by the way, this is called Fermat's theorem, right? Not Fermat's last theorem, Fermat's theorem. Fermat's theorem. But how would you do this in multivariable calculus? So let's say you had some f xy, right? And you wanted to find. I want to find the maxima and minima of f on a particular domain, right? I want to find the local, this is important, the local maxima, right? We'll see why this is important later, why the word local is important. Okay, so if that is the case, if it is the case that we want to find the local maxima and minima, what we need to do is we need to set the partial derivative of f with respect to x equal to 0, and the partial derivative of f with respect to y equal to 0, right? So if these two guys are equal to 0, then AB is either a local maxima or a local minima, right? Maximum or local minimum. These are plurals actually. Maximum or local minimum, right? Now, this is theorem 2 from your book. Now, why is this true? Why is it that when the partial derivative with respect to x is 0 and the partial derivative with respect to y is 0, why is it that then AB is a local AB then f has a local then f of AB is a local maximum or minimum, right? Not AB. AB is the point at where you have your local maximum or your local minimum, right? Okay, so of course we're assuming that the partial derivatives, they exist at AB. Okay, so how do we prove this? Let's prove this first, right? let g of x equal f x and v, right? So what we did was we set y equal to some constant. Now since y is constant, f is just a function of g is just a function of x, right? Now if f has a local minimum or maximum at AB, what must be true? G prime of x must be equal to 0, right? And by G prime of x we mean dg over dx, right? And 0 at a, at x equals a. So this tells me that dg over dx x equals a equals 0. But then df over dx, but then this is, of course, this is equal to partial f over partial x at ab. This implies partial f over partial x at ab equals 0, right? And of course you have and then you let g of, actually let's not call this g, let's call this h. H of y equals f of a comma y. So h is a function of y only, right? And that tells me that at AB, h prime of y equals 0, which tells me that fy at AB equals 0, right? So this is similar to the first one, right? This is fx of AB equals 0. So f sub x of AB is 0, and f sub y of AB is 0 at the critical point, right? At the local maxima or local minima. Great. So what do we do next? We do an example next. Okay, so notice something here. Remember that the equation of tangent plane is equation of a tangent plane is at x naught, y naught, z naught is what? Is z minus z naught equals fx x naught, x minus x naught plus fy, y minus y naught, right? Now of course this is evaluated at x naught, y naught. It's also evaluated at x naught, y naught. Now if fx and fy are both 0, then z equals z naught. What does that mean? What is the geometrically? This means that the tangent is parallel to the xy plane, right? The tangent is the xy plane, and we have a constant tangent that is parallel to the xy plane. This is similar to the tangent plane is parallel to the xy plane. So in single variable calculus you have the tangent line being parallel to the xy plane, right? No, it's parallel to the x-axis, right? So this is a tangent line. Tangent line at critical points are parallel to the x-axis, right? Tangent lines at critical points are parallel to the x-axis, right? Okay, so if, right, in multivariable calculus, right, if you have fx at ab equals 0 and fy at ab equals 0, or either fx at ab or fy at ab does not exist, then AB is known as a critical point, right? AB is known as a critical point. Now this is extremely important. What I'm about to say is extremely important. If both partial derivatives are 0, right, then the point where the partial derivatives are 0 is known as a critical point, right? But just because it's a critical point doesn't necessarily imply that it's going to be a maximum or a minimum, right? A critical point is not necessarily a maximum or a minimum, right? Now, if it's a maximum or minimum, then it's a critical point, right? So critical points could be, so you could have so critical points, they could be in multivariable calculus, they could be maxima, they could be minima, and you can have something called a saddle point, which we will come to later, right? So a critical point can be a maxima or a minima or a saddle point. Now let's look at a few examples of critical points, and then we'll find a way to determine if a critical point is a maxima or minima or a saddle point. Okay, so let f of xy be the function x square plus y square minus twice x minus 6y minus 14, so plus 14. Then f sub x of xy equals twice x minus 2, and f sub y of xy equals twice y minus 6. Now at the critical point, both fx and fy are equal to 0. So it tells me that at the critical point x equals 1, i.e. x equals 1 and y equals 3. So 1, 3 is a critical point. Now we don't know yet if this critical point is a maximum or a minimum or a saddle point, right? We do not know if this critical point is a maximum, a minimum, or a saddle point. It could be any of these three, right? Now let's try to write f in another fashion, right? So you have f of x equals 4 plus f of xy, right, which is the original graph, right? So f of xy. This can be written as 4 plus x minus 1 whole square plus y minus 3 whole square. Right, so if that is the case, at the critical points, f of xy equals 4 at the critical point, right? F of xy equals 4. Now notice something here. F of xy equals 4 and f xy is greater than or equal to 4 in general. Why? Well, that's because if this has a minimum value of 0, this has a minimum value of 0, I know equals 0, and so this must be at least 4. F of xy must be at least equal to 4. So what does that tell me? That tells me that that 4 is the minimum value of f of xy, and once you see that, you see that 1 3 is a local minimum. F of 1 3 is a local minimum. In fact, we know for a fact that the domain of the function, right, it extends throughout R2, and we have one local minimum, right? So we can safely say that f of 1 3 is a global minimum, right? Have a look at the shape of the graph of f. Sorry, not 1 2 1 3, I think. Yeah, 1 3. Right. So this is the point 1 3 4. Right. So this is the shape of f. Okay. So and then we'll see an example of a graph with a saddle point. Okay. So the equation given is f of xy equals y square minus x square. Now notice that if I traverse this graph, if I go along this graph along the x-axis, right, I go down, 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 and then I start going up, right? So viewed from someone going along the x-axis, along the y-axis, I hit a minima, right? But the same point viewed by someone moving along the x-axis is a maxima, right? You go up and then you go down if you're going in that direction, right? So a saddle is something that is a maxima. A saddle point is a point that is a maximum if you're going in one direction, and a minimum if you're going in another direction. right? It's just like a mountain pass or a valley of sort. Yeah, a mountain pass, right? So moving, which has the shape of a saddle, right? So this is why it's called the saddle point. This is the plot of f xy. So this is the point 0, 0, 0, of course 0, 0, 0, and you have f. So fx equals negative twice x, fy equals twice y. So the critical point is 0, 0. And of course, at the saddle point is neither a maximum or a minimum. Right? Now, how do we ensure that a point we're talking about is a saddle point? Well, there's some, just like you saw in single variable calculus. There is a second derivative test in multivariable calculus. Right? It's called it's named the second derivative test. So let's say at AB, I'm going to give you the proof of this during consultation, right? So let's say f of AB equals 0, fx of AB is 0, and fy of AB is 0, right? And you don't know how to, and you want to find, what do you want to find? You want to find the nature of these critical points, right? So you know that this is AB is a critical point, but you want to find the nature of this critical point, right? So we set up something called the Hessian of f, right? Hessian of f at AB. So the Hessian is nothing but a determinant, right? This is a determinant. This is a determinant. So let's call this D, and this determinant is basically equal to fxx AB fxy AB fyx AB fyy AB, which is equal to fxx AB fyy AB minus, now since fxy is the same as fyx for the functions that we will be considering, this is equal to fxy AB squared, right? Okay, so we call this quantity D, capital D. Now the second, according to theorem 3, f has to be continuous on a disk with center AB. F is continuous on a disk, center AB, right? And of course, fx at AB is 0, f sub y at AB is 0, and then we define the Hessian matrix. Now, if the Hessian is greater than 0, if D is greater than 0, and fxx AB is greater than 0, then AB is a local minimum. If D is greater than 0 and fxx AB is less than 0, then AB is a local maximum, right? In fact, I should be calling this D at AB, right? D at AB. because d is a function of a and b. D is a function of x and y, but we're evaluating at a and b, right? Now, if d is less than 0, if d of av is less than 0, then av is a saddle point of f. Now, if d is equal to 0, we have no further information. We have no further information, right? It could be a maximum, it could be a minimum, it could be a saddle point. Okay, so using the second derivative test, what we can do is we can systematically find the maxima, the minima, and the saddle points. Okay, so let's do the second derivative test on some of the examples given in the textbook. Let's go through some of them. So, for example, if you have, let's first do, okay, let's do example 3 from the textbook. Find the local maximum and minimum values and saddle points of, given your fxy equals x to the 4 plus y to the 4 minus 4xy plus 1. Okay, so the first thing you do, of course, you need to find the partial derivatives and set them equal to 0. So fx xy equals 4x cubed minus 4y, and fy xy equals 4y cubed minus 4x. So these are the partial derivatives, right? So fx xy equals 0 and fy xy equals 0 at the critical points, right? So that tells me that y equals x cubed and x equals y cubed, right? So and of course you can solve this by so if x equals y cubed, then y equals y to the 6th power. Sorry, y to the 9th power. And this gives you y 1 minus y to the 8th power. 1 minus y to the 8th power equals 0, or y equals 0 and plus minus 1, because that's the 8th root of, so it's because we're taking an even root of 1. Right, now if that is the case, then if y is equal to 0, x equals 0, y equals 1, x equals 1, y equals minus 1, x equals minus 1. So we have 3 critical points. 3 critical points. They are the origin, the point 1, 1, the point -1, -1. 3 critical points. Now, let's examine each of the. Let's examine the Hessian at each of them in turn. Of course, for that we need to take all the find all the second derivatives, right? So fxx at xy, we need fxx, fxy, and we need fyy. Right, so fxx at xy is of course -4. Fyy at xy, I'm sorry, fxx is 12x, so not -4, 12x. going to guess this is 12y as well. This is 12y, right? 12x, 12y, and this is xy, right? So you take x first and then y, -4. So what is DAV equal to? So what is D of xy equal to? The Hessian at xy. This is equal to 12x, 12y, minus this is xy, so not yy. And this should be yy. 12x, xx, yy, minus f of xy squared. This is 144 xy minus 16. Right? Now let's go back to our second derivative test, right? And let's test for the second derivative at each of these 3 points, right? So let's look at 0, 0. At 0, 0, at 0, 0, what do we have at 0, 0? D of, okay, let's look at D of 0, 0. D of 0, 0 equals -16, which is less than 0. So by the second derivative test, the third case, right? Second derivative test, third case. Just a moment. Okay, so if D is less than 0, then AB is a saddle point of F. Now, it doesn't really matter what the values of fxx or fyy are, as long as D is equal to 0. As long as D of 0, 0 is less than 0, we have a saddle point. So 0, 0 is a saddle point. Right, and then you have D of D of 1, 1, right? So D of 1, 1 equals 144 minus 16, which is 128. Now, which is greater than 0? Yes. Now, remember, if D is greater than 0, what did I write down the criteria? Right. Now, D is greater than 0, fine. But what is fxx? Let's find fxx at 1, 1. Fxx at 1, 1. So fxx is 12x, right? So this is equal to 12. Again, this is greater than 0. Now D is greater than 0, fx is greater than 0. This tells me that f of 1, 1 is a local minimum, right? And similarly, D of minus 1 minus 1 minus 1 minus 1 equals this is actually also equal to 128, which is greater than 0, and fxx at minus 1 minus 1, this is equal to negative 12, right? This is equal to negative 12, and which is also greater sorry, it is less than 0. No, this is equal to 12. I'm sorry, not negative 12. This is equal to 12, which is greater than 0. So f of minus 1 is a local minimum also. Now, so we have 3 points, right? 0, 0, which is a saddle point. 1, 1, which is a local minimum. Negative 1, which is a local minimum. And let's look at the plot of this function. And you have, okay, just give me a moment. I think it should. Let's look at the plot of this function. So this is so this is this point is, I think, yeah, this point is 1, 1. This point is negative 1, negative 1. So this is a local minimum, and of course this point here is 0, 0, right? So this is a local minimum. Local minimum. This is a local maximum, and this is a saddle point. And we could let's look at another example where we need to classify the critical points of the function 10x square y minus 5x square minus 4y square minus x to the 4 minus y to the 4. The first thing you do is you set the critical you set the partial derivatives with respect to x and with respect to y equal to 0, and you get this equal to 0, this equal to 0. You solve them, and you get you solve those equations, and you get the point 0, 0 plus minus 2.6 for 1.90 and 0.86, 0.65, and you find f, you find fxx, you find d. So here fxs is less than 0, fxs is less than 0, fxs is less than 0, always, right? So, and d is positive here, so this has to be local maximum, right? These 2 points have to be local maxima, because d is positive but fxx is less than 0, but here d is negative, so it doesn't really matter what the sign of fxx is. This is going to be a saddle point. And the graph looks like this, right? So you have 2 local maxima and you have a saddle point. So during concentration, we're going to try to plot this in Matplotlib, and I'll show you the saddle points. Have a look at this example. Find the shortest distance from this to the plane. Okay, so this is applied stuff, all right? So if you want to find the shortest distance from a point to a plane, well, of course, the shortest distance is the perpendicular distance, right, from a point to a plane. So the shortest distance would be the distance along the perpendicular to the plane. Right now, so we could solve it that way. We could solve it using vector methods, but we could also solve it using what we've learned here, right? So, okay, so when we're dealing, so we want the shortest distance. What shortest distance do we need? We want the shortest distance from what point to what plane? Let's have a look. We want the shortest distance from the point 1, 0, negative 2 to the plane x plus 2y plus z equals 4. Z equals 4. So this is example 5, worked out example 5 in your textbook on page 1013. Example 5, page 1013 in your textbook. Right. So so what is the distance from a point to another point? Right. So the distance is of course given by distance from the point D. Okay, let's call this point P. Distance from P to the point x comma y comma z. Right. So this is equal to x minus 1 square plus y square plus z plus 2 square. Right. Now we want to minimize this, right? We want to minimize this. We want to minimize this distance because we want the shortest distance, right? Now, if d is a minimum, then d squared is also a minimum, right? D squared is also a minimum, right? So what is d squared equal to? If d is a minimum, then d squared is also a minimum. But d squared, why do we want to work with d squared? It's because we have a square root, and square roots are annoying. We want to get rid of square roots. So d squared equals x minus 1 squared plus y squared plus z plus 2 squared. And of course we want to apply the fact that the point xyz is on a plane, right? So it's constrained by this equation, meaning z equals 4 minus 2y minus x. So d square is actually a function of just x and y. X minus 1 square plus y square plus 6 minus 2y minus x square. So we want to find the derivative of this guy with respect to x. We want to find the derivative of this guy with respect to y and set those equal to 0. Sorry, it's writing too fast. We want to find the derivative of this d squared with respect to y and with respect to x and set them equal to 0. Alright, and that will help us find the shortest distance, hopefully. So this is actually equal to 4x plus 4y minus 14. 4x plus 4y minus 14. And this is equal to 4x plus 10y minus 24. Now setting these guys equal to 0 gives me one critical point, 11 by 6. Solving these two equations simultaneously gives me x equals 11 by 6 and y equals 5 by 3. This is worked out in the book. So anyway, at this point, d square xx of xy equals 4 d square yy at xy equals 10 and d square xy at xy equals 10 equals 0. No, not 0, sorry. 4. Right? Now the Hessian at xy is of course d square xx times d square yy times d square xy square, right? So you have d square xx d square yy minus d square xy square, which is equal to 4d minus 16 just 24, which is greater than 0. Now actually let's not call it h for the Hessian, let's keep it at d, right? Since we're using the notation d, let's keep it at d, right? So if this is greater than 0, and of course d square xx is greater than 0, that tells me that the point here is a minima. Is a point where d square is a local minimum, right? So the shortest is, so if x equals 11 by 6 and y equals 5 by 3, then d, remember d is given by the square root of x minus 1 whole square plus y square plus z plus 2 whole square. So we know z from x and y. So remember, d is given by the square root of x minus 1 whole square plus y square plus 6 minus 2y minus x square. That's y square plus 6 minus 2y minus x square. Now you plug in x equals 11 by 6 and you plug in y equals 5 by 3. You get d is equal to, you're going to get d equals 5 over 6 root 6. So that is the shortest distance from the point P to the plane given by x plus 2y plus z equals 4. So I would also advise you to look through example 6, work through it. Right? Work through example 6. Okay, now so far we've been looking at local maxima and minima. But what about absolute maxima and minima, or global maxima and minima? Right, so the definition of an absolute maximum, and of course minimum, is this. So you let f a b. So you have a function. I'll explain the definition. Let's go over the definition, and I'll explain it later. I'll explain it right after. Okay, so just as with single variable functions, you can have absolute maxima and minima for multivariable functions. Right? So so you have so you have a function ab, which is a point ab in the domain of a function f of two variables. Then fab is the absolute maximum if the value of f on D, if fab is greater than or equal to fxy for all xy in D, right? And it's an absolute minimum on D if fab is less than or equal to fxy for all xy in D. So have a look here. In this first example, right? This is an absolute minimum. This is an absolute maximum. That's because they're absolute maxima and minima on the entire domain, right? And of course and this is a local maximum, and this is so this is a local maximum, this is a local minimum, because they are maximum and minimum on subsets of the domain in small neighborhoods of the critical points, right? So okay, so this was the case in single variable calculus as well, where you had a global minimum. So this is a global maximum, global or an absolute maximum. This is a global or an absolute minimum. Again, but this is a local. These are local maxima, right? These are local maxima. And this is a local minimum, right? So okay, so so for function, so we've looked at the function of one variable, right? And now let's see what happens with functions of multiple variables. So you have you've already looked at open sets and closed sets of remember, if you recall from functions of a single variable, you have an open interval AB. What does this imply? Of R, right? So this implies that A x V. You could have it open at one end, right? A x V, or you could have it closed, open interval. This is open at one end, and this is closed interval, right? A comma V, which is such an R, which is the same as A V, right? And similarly, in when you're dealing with functions of two variables, you can have open sets or closed sets of the inside the domain, right? So an open set is a set that does not contain its endpoints, right? So for example, these are not closed sets, but okay, I'll tell you what. A closed set is one that contains all its boundary points. A closed set is one that contains all its boundary points, right? So this disk and this square, they're closed sets because they contain the boundaries that they're on. Or for example, the disk. So the disk D, right? This indicates all points. All points. Sorry. All points on and inside the circle, inside the unit circle centered at the origin, right? And of course so that's that's a closed set, right? This D is a closed set. Now a bounded set is of course is one that is contained within one disk, right? It's finite. It may be open or not, but it is within a disk, right? Okay, just to clarify, open sets are not the opposite of closed sets. This is something you'll look at again in topology, right? So there are sets that can be both open and closed at the same time. They're called clopen sets, C-L-O-P-E-N, clopen. Right? So open sets are not the opposite of closed sets. Right, so this is a bounded set. So let's look at the extreme value theorem for functions of two variables. Right? Extreme value theorem for functions of two variables. And you'll see why we've defined the open and closed. You see why we've defined open and closed sets right now. So, if f is continuous on a closed bounded set, meaning if it is closed, meaning it contains its endpoints, right? And if it in R2, right? Let's say the domain of f is D, right? The domain of f is D. So D is of course a subset of R2. Now, f will attain if f is continuous on a closed bounded set D in R2, then f will attain an absolute maximum value, and f will attain an absolute minimum value somewhere inside D, right? F is going to attain an absolute maximum value. F is going to attain an absolute minimum value inside D. This is guaranteed, right? By now, you're probably familiar with the extreme value theorem in one dimension, right? This is the extreme value theorem in two dimensions. We're not going to prove this theorem. We're going to take this theorem as a fact, but the proof isn't all that difficult either, right? So, so we are going to have the absolute maximum and absolute minimum on that closed bounded set, right? So, which is a subset of R2. Now, if you want to find the absolute maximum and minimum of a continuous function on a closed bounded set D, then what you need to do is you need to find the values of f at the critical points, and then find the extreme values of f on the boundary of D, right? And then you need to compare the critical points and the boundary, and once you and whichever is the highest or the lowest is the maximum or the minimum, right? So is the absolute maximum or the absolute minimum, sorry. So you said closed bounded set, right? So bounded set is of course one which is contained within some disk, right? So for example, this rectangle, it can be contained within a disk. Okay, so let's look at this example, and with that we will finish the lecture. Okay, so I'll work it out separately. Okay, so just a moment. So we have the function fxy equals x cubed minus twice xy, sorry, x square equals x squared minus twice xy plus twice y. And we want to find the absolute maxima and minima of f on the domain that is given by okay, so D for domain, D for Hessian, D, which is the rectangle 0x3 0 y 2. Right, so if you're going to find the absolute maxima or the absolute minima, what you need to do is you need to be given a domain first. Okay, so what was step 1? Step 1 was find. Now notice that f is continuous. This is a polynomial function of x and y, and f is continuous, hence f is continuous. So by the extreme value theorem, right, it's continuous and is on a closed bounded set D in R2. So our set is bounded, right? Our set is this rectangle. It is bounded, and f is continuous. So f must have an absolute maximum and an absolute minimum in D. That has to be the case. This has to exist. Right. So let's try to figure out what the absolute maxima and absolute minima are. So let's sketch the domain first. Let's sketch the domain of f. Right. So 0x3, 0y2. Let's draw the rectangle. Okay, so it's bigger in the x direction and the y direction. Okay, fine. So this is the domain. So this is the domain D. Right. So this is the line y equals 2. This is y equals 0. The x-axis. This is x equals 3, and this is x equals 0. Right. Now, inside the domain, let's look for the critical points that are inside the domain. So f sub x of xy equals twice x minus twice y, and f sub y of xy equals minus twice x plus 2. And you set these guys equal to 0, and you get x equals 1, y equals 1, right? And f of 1 1 equals 1. Right. So you have okay. Now is 1 1 inside the domain D? Yes, 1 1 is within this rectangle. 1 1 is somewhere here, right? So 1 1 is inside D. Okay, now let's check out the values of f on the borders of the domain, right? Now, if x equals 3, f of 3y f of 3y equals 9 minus 4y. Right, for y going from 0 to 2. Now, what is the maximum value of this guy? Well, the maximum value is 9, right? Maximum is 9. Minimum is 1, right? So that is the maximum and minimum value of f on this edge, right? So you have max 9, min 1, right? So that's on the edge. And then you have how about here? If y is equal to 2. So f of x comma 2 equals what? X square minus 4x plus 4, x squared minus 4x plus 4. 4x plus 4, which is equal to x minus 2 whole square. So x can go from 0 to 3, right? X can go from 0 to 3. So the maximum value is, of course, when the absolute value of this is the highest, of x minus 2 is the highest, which is when 3 minus 2 is 1. Actually, 0 minus 2 is 4, yeah, 4. The maximum value is 4. And the minimum is, of course, 0. Right, so the maximum is 4 and the minimum is 0. And now let's see here, max is 4, minimum is 0. What over here, where x equals 0? Well, if x equals 0, then f of 0y is equal to 2y. F of 0y equals 2y, where where y varies from 0 to 2. 0y 2. So max here is 0. Max here is 4. Min is 0. Here as well. Right? Max is 4. Min is 0. And what about this boundary where y is equal to 0? Well, if y is equal to 0, then we have x squared, fxy, fx0 equals x squared. And of course x goes from 0 to 3. X goes from 0 to 3. So then max equals 9, min equals 0. Right? So here max equals 9. 9. Min equals 0. And here on this edge, max equals 4. Min equals 0. Okay, so you have f being maximum on this, and if you compare, if you want to find the maximum, right, of f, the global maximum, the highest of the maxima are on this edge and on this, on this side and on this side of the boundaries of the domain, right? 9, right? So f max equals 9 on D. What is the minimum, right? What is the minimum value that f can take on this domain? Well, it's 0, right? Here and here and here. So f min equals 0. So these are the absolute maxima and minima. Absolute maxima and minima of f on D, which is of course a subset of R2. Alright, so that about does it for this lecture. This was 14.7 from your Stewart's Calculus textbook. Our next lecture is going to be finding maximum and minimum values with specific constraints. So that's going to be your section 14.8 from Stewart's Calculus. All right, then I will thank you very much. I will see you on, inshallah, on Monday.